So we're recording now. All right. So we're gonna consider the non-homogeneous system x prime of t equal at x of t plus g of t. Let's say t bigger or equal to 0. Okay. And let me see what I call this one is 3.213. Okay. So here A is a matrix with n by n matrix with constant coefficient, with constant, variable entries. That are continuous on some interval r. And g of t is an n by n, n by 1 factor that is continuous on r. Okay? And so this is what we are looking at. So in order to solve 3.2.13, we must know how to deal with the homogeneous system x prime of t equal to atx of t. T bigger or equal to 0, and I assume 140. This is the same matrix A as in 3.2.13. Okay? Is the picture okay? All right, I assume it is. So last time we looked at higher order differential equation and we saw how to put them into a system. So when you can write them like this or like that, if they're homogeneous. So from now on, we're gonna try to see how we can solve them. Okay? All right. We're gonna have a definition, and this is definition 3.23. Okay? A set of functions excuse me, fi, I equal 1 to n, that is continuous on a set I is said to be linearly dependent if there are constant Ci, I equal 1 to n, not all 0, so that C1 F1 plus C2 F2 plus Cn Fn equals 0 for all t in I. Okay, let me read it again. A set of functions fi I equal 1 to n that is continuous on an interval I is said to be linearly dependent if there are constants ci I equal 1 to n, not all 0, so that C1 F1 plus C2 F2 plus Cn Fn equals 0 for all t in R. Okay? Any questions? Now, if C1 F1 plus C2 F2 plus Cn Fn equal to 0 only for C1 equals C2 equals Cn equals 0, then Fn is said to be linearly independent. Okay? So that means if this only hold for all the CI's equal 0, then the set is said to be linearly independent. Okay? For example, if I take e to the t and 2e to the t, so this is linearly independent, linearly dependent. Since C1 e to the t plus C2 times 2e to the t equals 0 for C1 equal -2, C2 equal 1. So they're linearly dependent. Okay? On the other hand, e to the t, e to the minus t is linearly independent. Since C1 F1 plus C2 F2 equals C1 e to the t plus C2 e to the minus t equals 0 if and only if C1 equals C2 equals 0. And remember, we need that for all t. All right? Okay? All right. Another way of looking at this is define W of F1, F2, Fn by the determinant F1, F1 prime, okay? F1, let's see, F1 prime, F2 prime, all the way to Fn prime, F2, Fn prime. This is the determinant, okay? then Fi is linearly independent if and only if W of F1, F2, Fn is not 0. So this is if and only if statement. Okay? So that means, so this is linearly independent if and only if the determinant is non-zero. That means if the determinant is 0, it's not linearly independent. That means it's linearly dependent due to the if and only if statement. For example, if you take this one, you get e to the t, 2e to the t, 2e to the t, 2e to the t, and that is 2e to the 2t minus 2e to the 2t equals 0. So you see, we know that this is linearly dependent. Okay? On the other hand, if you look at this one, you get e to the t, e to the t, e to the minus t, minus e to the minus t, and that is minus 1, minus 1, that is minus 2, that is not 0. So these are linearly independent. Okay? So, and what I mean by here is this is the nth derivative. Okay? All right? This is Fn. And this is Fn. Okay? Any questions? No, there's a mistake here. This should be n minus 1. Okay? It should be n minus 1. All right? Okay. All right. So this is linear dependence, linear independence, and so forth. I'm going to skip to your 2.2, and I'm going to look at the fundamental matrix. All right. I'll be right back. Just a minute. Just finish this. Please come back. Daddy, you want to come say hi to the class? Come. You want to come say hi? Yeah? Come. Here's Lily. Come on. Come. Here is Lily. Good girl, Daddy. Good girl. You see? You want to look at the class? All right. We'll go back to our Lily. Okay. She said hi. All right. Now we're going to look at different concept. Okay. Remember, x prime of t equal at xt, t bigger or equal to t naught bigger or equal to 0. This is 3.2.14. Okay. This is definition 3.2.4. This is about the fundamental. set of solutions. Okay? A set of n solutions, okay, of 3.2.14 is called a fundamental set of solution fundamental set of solution on an interval I if the solutions are linearly independent. So basically, the functions phi 1 of t all the way to phi n of t form a fundamental set of solution of 3.2.14 if A each phi I of t, I equal 1 all the way to n, is a solution of 3.2.14, and B, the set phi I of t, I equal 1 to n, is linearly independent. Okay, so this is what the definition says. All right. So go ahead and let's solve x second of t plus, or may I say, minus 9x of t equals 0 for t bigger or equal to 0. Go ahead and solve this differential equation. See what you get. All right. Well, the solutions are, so you'll have, if you look for solution of the form e to the mt, then you got m squared minus 9 equals 0, m equal plus or minus 3. So your set of solution is e to the 3t, e to the minus 3t. Now each phi 1 equal e to the 3t, phi 2 equal e to the minus 3t solves the differential equation and linearly independent. So this set form a fundamental set of solution. This is a fundamental set of solution for this one. Okay? So the requirement that each function has to be a solution, and the whole set of solutions has to be linearly independent. All right. Any questions? Oh. All right. Now we're going to look at different concept. This is corollary 3.2. So it says if phi 1 of t, phi 2 of t, phi n of t form a fundamental set of solution of 3.2.14, then it's a general solution takes the form x of t equals c1 phi 1 of t plus c2 phi 2 of t plus cn phi n of t. Okay? So, all right. So basically the other system, x9 minus 9x equals 0, you got x equals c1 e to the 3t plus c2 e to the minus 3t on the previous example, right? That is a solution. Okay. All right. So go ahead and try now x second plus 9x equals 0. See what you can do with that. Find the fundamental set of solution and the general solution. All right, so again, this will be m squared plus 9 equals 0, m equal plus minus 3i. So the solution is xt equals c1 sine 3t plus c2 cosine 3t. So this is your phi 1, this is your phi 2. You can show each one of them is a solution, and you can show they are linearly independent. Okay? All right. Now, another important formula. So I'm going to flip the board in a second.
Yeah, I can definitely.
You can do both if you like to. All right. So let's flip the board. So we defined the fundamental set of solution. Now we're gonna take a look at the fundamental matrix. And this is definition 3.2.6. This is called the fundamental matrix. Okay? A matrix solution, and you see how I am writing this as phi, is called a fundamental matrix solution or fundamental matrix or fundamental matrix of 3.214 on an interval I. Okay? If its columns form a fundamental set of solutions, okay? If in addition phi of T naught equal I, then the fundamental matrix solution is called the principal fundamental matrix solution. Or simply, or principal matrix. All right, so now we're getting into the little nitty-gritty stuff. Okay. All right. I is the identity matrix. Here, I is the identity matrix. Okay. Remember before we had x second minus 9x equals 0, and we found phi 1 equal to e to the 3t, phi 2 equal e to the minus 3t, right? Now, if I take, or you can say x1 and x2. If I do change of variable, if I take x1 equal x and x2 prime equal to x prime, then x1 prime equal x prime equal x2, and x2 x2 equal x prime, and x2 prime equal x second equal to 9x equal to 9x1. Okay? So you will see how they are related here. So can you write, okay? Can you write this fundamental matrix from this one here? So we have x1 equal e to the 3t, x2 equal to e to the minus 3t, and here we have x1 prime equal x2, x2 prime equal 9x1. Okay? So what do you think? If you take x2 to be, so x1 prime equal to x2 equal e to the minus 3t, okay? Then x1 is minus e to the minus 3t over 3. So we may have two different set of solution, and x2 prime equal to 9x1, 9 e to the 3t, then x2 is 9 over 3 e to the 3t. So I believe your phi is gonna be e to the 3t, e to the minus 3t, and e to the minus and minus e to the minus 3t over 3, and 3 e to the 3t. That will be your phi. But this is a special case here. Okay? We said each, what did we say? We said each, remember, a matrix solution phi is called a fundamental matrix solution or fundamental matrix on an interval I if its column form a fundamental set of solution. So what does that mean? Its column. So let's call phi1 equal to e to the 3t, e to the minus 3t, and phi2 is e to the minus 3t over 3 and 3 e to the 3t. So what we know is from here, we have to have x prime equal a. We must have, phi 1 prime equal a phi 1, phi 2 prime equal a phi 2. This is what it means each column to be a solution. And remember, what did we have? We had x1 prime. Oh, did I erase it? Can somebody read me this? X1 prime was x2. X2 prime was 9. X1, is that right? I believe that. Okay. So what is the matrix A? The matrix A is 0, 1, 9, 0. So this system is written as x prime equals 0, 1, 9, 0 times x1, x2. Okay? So let's take a look at this one. What is a phi 1? That is 0, 1, 9, 0 times phi 1 e to the 3t e to the minus 3t. Okay? Let's see. Maybe I wanted to take it differently. Oh, phi prime. All right. So what is that equal to? That is e to the 3t. No, e to the minus 3t. E to the minus 3t. Okay? And 9 e to the 3t. So I did get my stuff mixed up, but that's all right. I will explain to you in a second. I should have taken the other way around. So what you need to show is phi 1 prime equal a phi 1, phi 2 prime equal a phi 2, and you should be okay. E to the minus 3t a phi 1 equal phi 1 prime. I got this component mixed up, but I will figure it out later. And so, or you can take the transport, which is okay, no problem if I take the transport. So we will get back to that notion later on in details. But for now, I just wanted to do a second order differential equation and show you how it all works. Okay. All right, let me see where I am. So this is what it really means. So all you need to know, if this matrix phi, the column is phi 1, phi 2, this, then you should have phi 1 prime equal a phi 1, phi 2 prime equal a phi 2, and so forth. Okay? So what else do we have? Now you can show easily that phi prime equal a phi for this one here. You can show that too. Okay. All right, let me go back to okay. So again, we're looking at x prime equal ax. let's take a look at xt naught equal x naught. Okay. So theorem 3.2.4, the matrix phi is a fundamental matrix of x prime equal ax at t naught if and only if a phi is a solution of x prime equal ax and b determinant of phi is not zero. And this is at t naught is not zero. Okay. The proof is in the book. I'm not gonna do it. All right. Now, condition B is equivalent to the linear independence of phi 1 of t naught, phi 2 of t naught, and phi n of t naught. Okay? All right. And these, the phi 1 are the column of phi, where phi I equal 1 to n are the columns of the matrix phi. Okay? All right. Let's do an example. Let's consider x prime equals 0 minus 1, 1 minus 2, x. And here x is x1, x2. Okay? For now, we just verify instead of obtaining that phi equal to e to the minus t minus e to the minus t, t e to the minus t, and 1 minus t e to the minus t is a fundamental matrix. is a fundamental matrix of this system. Okay, so what we need to do is, so A is 0 minus 1, 1 minus 2. Okay? So all we need to do is, the theorem told us, if we use the other theorem, so what is phi prime? Phi prime is minus e to the minus t, e to the minus t, e to the minus t minus t, e to the minus t, and will be minus e to the minus t minus 1 minus t e to the minus t. So I'm taking the derivative. Okay? And if I simplify this, this is minus e to the minus t, e to the minus t, e to the minus t minus t, e to the minus t, minus e to the minus t, and minus e to the minus t, I have minus 2 e to the minus t plus t e to the minus t. Now let's check a phi. That is 0, 1, minus 1, minus 2 times e to the minus t, t e to the minus t, minus e to the minus t, 1 minus t e to the minus t. And that is, if I multiply, this will be 0, this will be minus e to the minus t, and this will be 1 minus t e to the minus t. And let's see, did I forgot how to multiply matrices, for God's sake. All right. This is minus. So if you have, so why don't you go ahead and multiply these two matrices? See what you'll get. I'm gonna let you do it. I just gotta get a drink of water. I'll be right back. Multiply these two matrices. All right, so that is gonna be, if you multiply this with that, minus e to the minus t, if you multiply this with that, will be 1 minus t e to the minus t if you multiply here, you will have minus e to the minus t plus 2 e to the minus t will be e to the minus t, correct? And then if you multiply this together, will be minus t e to the minus t minus 2, 1 minus t e to the minus t. And you can see that minus t plus 2t, that will give you t, and minus 2. So this is phi prime. Okay? So we have shown phi prime equal a phi. All right? So this is A. We verified A. For B, if we look at the determinant of phi t naught at any t naught, so what we're going to get? We're going to get e to the minus t naught times 1 minus t naught e to the minus t naught plus t naught e to the minus 2t naught. Okay? And what is that? That is e to the minus 2t naught minus t naught e to the minus 2t naught plus t naught e to the minus 2t naught. This and this cancels, and you will get e to the minus 2t naught, and that is different from 0 for all t naught in any interval r. Okay? So this is indeed a fundamental matrix of solution. All right? Okay. Just dwell on it for a second. See, you see what we did. Okay? All right. Any questions? Any questions? Okay, well, let's continue. This is theorem 3.2.5 if phi is a fundamental matrix of 3.2.14, then phi of C, where C is an n by n matrix, n by n arbitrary non-zero, non-singular mean determinant of C is not zero, constant matrix. Is a fundamental matrix of 3.2.14. Conversely, if is another fundamental matrix to 3.2.14, then there exists a constant non-singular n by n matrix C such that C equal phi C for all t in R. Okay? So the idea is, if you know this phi is a fundamental matrix, then there is a constant matrix n by n C, so that the product, this may not commute, by the way, is also a fundamental matrix. Conversely, if C is another fundamental matrix to 3.214, then there exists a constant non-singular n by n matrix C such that C equal phi C. All right, so look, when you see when we did x second minus 9x equals 0, we got phi 1 is e to the 3t is a solution. Also, C phi 1 is a solution. Check it out. Put C phi 1 is also a solution. So basically, any e to the 3t a prime minus 9 c e to the 3t, that is equal to 3c, okay? Oh, second, 3c e to the 3t prime minus 9c e to the 3t, and that is 9c e to the 3t minus 9c e to the 3t, and that is 0. You see that? So this is, we're carrying the concept from a scalar to the fundamental matrix. That's all what we are doing. Take a look at the theorem, careful look at the theorem, and we'll come and prove it, because you learn something from the proof. All right, any questions? Any questions? All right, let's start the proof. Okay. The proof. Let consider phi c. Then phi c prime equal to phi prime c. Phi prime is at phi times c, right? Phi prime, if you look here, phi prime satisfies this, that's a phi from here. This comes from here. And that is at 5c. Hence, 5c solve 3.2.14. Now, since determinant of phi c equal determinant of phi times determinant of c, this is different than 0. Why? Because this is, we know this is different than 0, and the determinant of c is different than 0, because phi is a fundamental matrix. And so by theorem 3.24, by theorem 3.24, phi c is a fundamental solution, fundamental matrix of 3.2.14. Okay? Now we need to do the opposite, converse. Okay, so take a look at this easy proof. It's really simple. 3.214, the theorem, kind of give us the result, what we are really doing. It's really not hard. Now let's do the other part of the proof, conversely. Conversely. No, not the converse, may I say, but I wrote conversely. All right. Conversely, since phi inverse equal I, we have phi inverse prime that is equal to phi prime phi inverse plus phi inverse prime, and that is equal 0. Okay? So, or phi inverse prime equal negative phi prime phi inverse. And if I multiply by phi inverse, if I multiply multiply by phi inverse, and what do you get? You get phi inverse prime equal to negative phi inverse phi prime phi inverse. Okay? That's what we have. So this is basically, you may look at this as a formula on how to obtain the derivative of an inverse matrix. So basically, this is a formula on how to find the derivative of an inverse matrix, okay? That's what it is. Interesting, huh? So you start with this one. If you know the phi is non-singular. Okay? All right. So now let's consider or differentiate phi inverse C. So this is phi inverse prime C plus phi inverse C prime. Well, that is minus from here phi inverse phi prime phi inverse C plus phi inverse C prime. Okay? Let us factor C. There. Okay? What I did is, okay, so let me, this, I can do it by ATC. So this replace it by ATC, and so here you're gonna have you can have that because remember we know C prime equal ATC, okay, because it's a fundamental another fundamental matrix. All right, so what do you think we're gonna do now? We're gonna replace phi prime. This is minus phi inverse phi prime will be AT phi inverse a plus phi inverse AT C. Okay? Well, guess what? That is zero matrix. Why? Because A phi, you see this one, phi inverse is I. So you have minus A phi inverse A plus phi inverse A, that is zero. Okay, so we have shown that phi inverse C prime is the zero matrix. Integrate both sides. integrate both sides, you'll get phi inverse C, let's call it C. Multiply by phi to get phi equal to phi C. And there you go, guys. Okay? Do you see it? So note that in general, phi C is not C phi in matrices. So you have to be careful. This is the way you have to do it. So we are left to show what is the determinant of C. That is the determinant of phi C. That is the determinant of phi times determinant of C, and that is not 0. So by theorem, what is the previous theorem? 3.24. C equal to phi C is a fundamental matrix. Okay? Okay, I got two small things to cover, then I will stop. All right? Do you want me to change the ink? Is still dark enough for you? All right.
Before you erase the bottom section, I have a little bit of a quick question.
Yes, go ahead.
So how did you get, so at the bottom right, that I negative 1 AT, how did you get that? Is it just...
This one? Are you talking about this one?
Yeah, your conversion from like the bottom left to the bottom right. How did you get that AT in that one giant section?
Oh, AT here. Where?
Yeah. So how did you get it in that section?
Okay. This one here, right? From here to here?
From there to the right. So from the bottom left to the bottom right.
Yeah. But basically what I did is I went from here to here.
Mm-hmm.
Remember what we said? We said C is another fundamental matrix of x prime equal ATX. What does that mean? This means C prime equal ATC. So
Okay.
this C prime, I replaced it by ATC.
Okay.
You see what I mean?
Yep.
Then I factored C out. Okay? And
Yeah,
here,
and then,
I use the same thing here too. Okay?
So then you just said 5 prime is just A of 5 prime.
Yeah.
Okay.
Yeah.
Thank you.
Other questions? Okay, so this theorem also works when C is an n by 1 vector. So basically, if we have a solution, then we may write it as phi C, and this is a vector instead of a matrix. All right? Okay? So what I mean by that is, let us take a look at our example. Okay, well, let me do another theorem. This is, then I'll do an example, 2.7 theorem, sorry, 3.26. If phi is a fundamental matrix of 3.214 on an interval I, then phi c, where c is an n by 1 vector, solves 3.214. Yeah. You need me? No. So 3.214 with c is equal to C inverse of T naught X naught. So remember what 3.214, X prime equal AT XT, XT naught equal X naught. So now we need to find that constant. Well, let's take a look at it. Okay. Well, I mean, we can easily find. So if you look here, so we'll have phi prime C equal to A T X okay, let's take a look at phi as a fundamental matrix. Phi. Okay? We have phi prime equal A phi. And do I want to do it that way or should I do it another way? Okay. Well, we need to show xt equal atc is a solution. So we know x equal to phi t c is a solution. Now let's apply xt naught equal x naught. Remember, x naught is a vector. This is an n by 1 vector. So we have x naught, this is a vector, equal to phi t naught times c, or phi inverse t naught equal x naught. Phi t naught, phi inverse t naught x naught equals c. There we go. Okay. So this is how you determine your initial conditions, basically. And let me quickly take you back to this example we did. let me take you back to this example. X prime equal to 0, minus 1, 1 minus 2, x1, x2. And we know the solution, x of t, is phi. Remember what phi is back to this example, is e to the minus t minus e to the minus t, t e to the minus t, 1 minus t e to the minus t times x1, x2. So that is our solution. This is x1, x2. So this is your vector C. So let us say now at x of 0, we have minus 1 and 2. So apply it. So we have minus 1, 2 equal to 1, minus 1, 0, 1 times x1, 0, x2, 0, x1. Okay? So you may call this as your C. You may call this as C. So C is 1, 0, minus 1, 1 inverse times minus 1 and 2. There we go. That is your solution. Okay? So you need to find the inverse of this matrix times minus 1, 2. And then finally, your solution, X is, final solution, is this matrix, e to the minus t, minus e to the minus t, t e to the minus t, 1 minus t e to the minus t, times C. And what is C? This one. This is your C. Okay? All right? And now, at t naught, at t equals 0, you get x of 0 to be I. You will get I, believe it or not. All right. Well, actually, not I. You're gonna get x. You're gonna get minus 1, 2. Okay. But what I meant is, if you get phi of t, phi of 0, that will be I. Phi inverse of 0. So in other words, what is phi of t? E to the minus t minus e to the minus t, t e to the minus t, 1 minus t e to the minus t, times phi inverse of that times 1, 0, minus 1, 1 inverse, and that is gonna give you I. Okay? So this is the principal matrix. So this is you see as principal matrix solution. So this is your principal matrix solution, this one. You can check it. You need to find the inverse of that, multiply it, and you'll get I. Trust me. Okay? All right. I'm going to stop here for today. Any questions? Email me if you have any questions, please. All right?
So making sure when it's a midterm exam.
Does it really matter to you much, either Friday or Saturday, Sunday?
I would probably prefer Saturday and Sunday.
Okay, well, I think I'm gonna go for Saturday, Sunday,
Okay.
and so because I mean, if you open it on Sunday, you're gonna have to finish it on Sunday. You know what I mean?
Yeah.
So you need a day. That's all what you need.
Okay.
All right.
Thank you.
We'll talk. I'll talk to you about it more as tomorrow. Tomorrow is Wednesday. I'll talk to you a little bit about it tomorrow. Okay? And Thursday too. So we still have 2 days, tomorrow and Thursday. All right. Have a great day.